one of those components that we talked about earlier on in the chemistry, and it'll make components specific to these units. I'll take an isom, we'll take butanes, MTBE, today it's ethanol. So right now, legally, we can't put MTBE in, that's been banned here in the state of California. And now we're adding ethanol as an additive, and I'll show you why. And so we blend all these to make these premium, unleaded, mid-grade unleaded, which is your 89, 90, and then the regular grade, which is your 87 octane. And we blend them together with a little bit of LPG, which is your butane, in order to make these three different grades. What's important is that, you need to know, when you start getting into the premium grades, what makes it a premium grade are those specialty chemicals. You remember I told you the cyclic components and the olefins, because they have very high octane ratings. And as I pointed out last week, is that these are very chemically active components. With time, they do have a tendency to react with each other and form what are known as polymers or gums. You'll hear, oh, there's gum in your car. Okay, and someone will ask, well, where's the gum coming from? Well, the gum is coming from because you have some of these highly active chemicals, okay, that sit in your car for long periods of time. It will polymerize and form a gum with time. Because it's still exposed to air, and with air and these other components, it will react and form longer or bigger molecules. So my recommendation, if you do have a high performance engine, is make sure that you're always using the fuel. You know, it's going in and flushing it out. Okay? If you feel you're going to park the car for an extended period of time, you're safer putting in a lower grade octane and let it sit for 6 months or a year, or something like that. Normally you want to take it out, run it for a few hours, and then bring it back just to flush the engine out. Otherwise, you may subject yourself to gumming in your engine. Gasoline formulation, there's the regular and the premium, and look at the composition. Reformate, because reformate has very high octane and represents almost 60% of the gasolines out of reformer. While in your regular gasoline, you got 17%. And then they blend all this other stuff in there. Butane, which is that light component, 7% there. As I said, butane is important because you have to ignite the gasoline when they spray it. You have to be able to, it has to be able to catch fire. So the lighter components catch fire much easier than heavier components. Okay? But in this mix, look, you can actually put that LSR, which is light straight run. You remember that straight run that comes right off the crude unit at about 60 octane. But then I can blend it with alkylate, I can blend it with reformate, FCC gasoline, a little bit of butane, and we'll make that regular. And there's that R plus M over 2 that I talked about. You'll see that listed on most stations. It'll very little letters. Octane, number versus satisfaction. Of course, the higher the octane, everybody's very satisfied with the high octane gasoline. This is probably just a survey of users. And people, if you use very low octane, of course, you're not satisfied. You think there's something wrong with your engine. It's not performing, it's not picking up, it doesn't have the speed. Okay. Another thing, these are all factors that go into the operation and the function of an engine. Combustion chamber geometry, the fuel injection versus the old carburetors. Today, just about all the engines are fuel injection because you have the right volume, you have the nice spray nozzles that actually make sure that you have the right distribution, and they can actually inject it exactly where you want it, right on top of the pistons. And then the compression ratios, they play around with compression ratios. I don't know if anybody looked at engine sizes versus horsepower. There's some very interesting correlations, and some people don't understand. Well, why do the BMWs and the Mercedes-Benzes and the Volvos have such, why are they expensive? And they're expensive because the engines are designed for high compression, and with high compression you recover more energy. And if you try and correlate engine size, cubic feet or liters per horsepower output, you're going to find out there's big discrepancy between European engines and American engines. American engines, they seem to like the larger volume but low output, low energy outputs. Compared to European engines, they like them more compact, much smaller but very high ratios of power, like horsepower per liter. You know, like I have a 4.8 liter engine, there's like 300 horsepower, so it's about 60. But if you go to the European engines, they have like 2-liter engines, but it's got like, you know, like 200 horsepower out of it. It's like about 100 horsepower per liter, compared to 60 horsepower per liter in American engines. But they last longer because they burn at lower temperatures, lower ratios, and of course then it lasts longer. The guys that used to have Jaguars ages ago, the blocks were made out of aluminum, and with these high compression ratios, they didn't last very long. And everybody was taking out the old Jaguar engine and putting in a Ford engine, and that's why Ford ended up buying Jaguar now, and you have Ford engines in Jaguars. So. Compression ratios, turbocharging, that's a way of recovering heat, because you got that extra heat coming off the fuel after you burn it, and what they do is they turbocharge, they basically compress the air, and so you can actually get much higher compression ratios and recover more energy, so you get more power out of that. And then, of course, the deposits, you're burning a fuel, so, and it'll crack on you because of the high temperature that you're burning it at, so there will be deposits. And that's why you have a lubricating oil in order to clean your engines and your pistons and make sure that you don't get. And the net result is this knock here, does it knock or it doesn't knock, and how an engine functions. Okay? Gasoline volatility, how volatile a gasoline is, I think is important, because depending on how you fire the engine. So, fast warming, you want to prevent vapor lock. And we measure volatility by this term RVP, which is Reid vapor pressure. Reid was the name of the guy that invented this ASTM procedure for testing or measuring a pressure of a liquid, the pressure exerted by a liquid. It's a bomb, it's basically a cylinder. You open it up, you fill it up with gasoline, you close it, and then you put it in a bathtub of water at a fixed temperature, normally about 100 degrees, and then it's got a little gauge on it and measure the vapor pressure. Interestingly, that pressure is not the true pressure, because it's a blend of different components, and sometimes you've got humidity in the air, and you've got some other little factors that influence the vapor pressure. So there's a slight difference between what is measured as a Reid vapor pressure and a true vapor pressure. True vapor pressure, you really need the actual composition in order to predict the exact vapor pressure of a component. Or there are special tests that are used for predicting the vapor pressure. But this became very popular because it's very easy to run in a lab in less than an hour. Okay? And refineries use that a lot. We also look at distillation curves. When I take a cut, these towers that produce the gasoline and the different products, has a boiling range, 30, 40 through about 320, 380 degrees. And then the vapor to liquid ratios, these are things that we measure volatility with. We adjust volatility by season. In other words, in the summertime, it's hot, so the fuel in your tank is sitting there warm, and so we don't want too many vapors in it. So we kind of tone down. You'll see that Reid vapor pressures, the spec for gasoline in the summer is about 6 RVP. In the wintertime, it's cooler, much cooler, so you need to add more volatility. You need to add more lighter components, so we can go up to about 8 RVP. We can add more gasoline. And then engine requirements. Again, sometimes different engines have different requirements. Cars progressively improving cold and hot weather performance. I mean, with the fuel injection, it isn't really as sensitive as it used to be with old carburetors. So that's why I'm saying the fuel composition is really becoming much, much tighter in being able to control. Let me see. Yeah, so these are examples of like the RVP. These are different blends of crudes. Now, the blend also depends on the altitude, whether you're up in the mountains driving or downhill, because up at high altitudes, the vapor pressure should be much lower because you're at higher elevations, and so it's much easier to evaporate the fuel. And then different distillations. So the lighter the crude, you can actually, you notice, if you're trying to blend here a 9 RVP gasoline, you can actually tolerate some more heavy ends on the back end of the gasoline. So you'll see that the end point, that 90, the 10, the 50, and the 90 is actually the percent evaporated on those curves that I showed you with the percent vaporization versus temperature. So what we call the 90% point is at 374. Someone may ask, well, why 10 and 90? Well, they picked the 10 and 90 because if you get, it's got to do with the repeatability of the test. If you do the test 2-3 times, there's a chance that everybody will meet the 10%. The initial boiling point is very hard to predict or hit, and same thing with the end point. And so we just take the 90 and the 10%. Legislated RVP, again, as I said, the problem with the higher RVPs is you're putting in a light component, and you remember I talked about how when you're filling up your car with gas, you get vapors coming off the gas. So the lighter it is, the higher the RVP, the more hydrocarbons have a tendency to evaporate and then get into the air, and that affects the smog, and I'll try and address that shortly. The EPA has certain restrictions on RVP, depending on which state you're in, because of, again, climate conditions, because they are different. Every state has a different rules and regulations. And then lately we have the EPA Phase 2, which have more restrictive conditions for RVP. These show the different regions in the United States, and you can see the northern states represent basically the colder climate, and the southern states represent the warmer climates. And so you'll see that the RVP between summer and winter fluctuates somewhere between 7.8 and 9, depending on the season. And then in May, most areas there will have like a 9 API, May through September. And then from September through June, that's winter time, you'll have the higher RVP. Okay? These are different emission standards from different RVPs. Of course, the higher the RVP, you can see the emissions from your car are much higher. So the tendency now is to lower the RVP. In California, we have 6 to 8 between summer and winter. It's not as high. These are averages across the whole U.S. State. These are different problems with cars knocking as much as, the more vapors you have in a car. So if you have too much vapors, you have really a tendency to get a lot of knocking, and you get vapor lock from the pump to your engine, because you park your car, you let it sit, it warms up, and so if you have a tendency for any evaporation, you'll get vapors, and you'll see the car kind of shaking a little bit before it picks up again. Okay. Oxygenates. This was an interesting test. The chemical compounds that contain an oxygen atom, it's embedded in the chemical composition of the component as part of the chemical structure, and they're suitable for use as supplements or substitutes for current liquid transportation fuels. That's what they call an oxygenate. So the more popular oxygenate today is ethanol, simply because ethanol is biodegradable. You can drink it, nothing will happen to you other than just get drunk. And it's kind of funny, when we were converting a methanol to ethanol, we have to contaminate the ethanol tanks, because operators in a plant will have a tendency to go and steal or fill up a tank or fill up a gallon with I mean, it's a funny thing, but it does happen. People, oh, there's a tank of ethanol right there, so go take some ethanol with you home and make flash or make whatever. So we have to, I guess, denaturalize it, I think is the word. You'll hear that term a lot. And they just pump a little bit of gasoline into it so that when you drink it tastes really bad. It won't kill you, but it's okay. Just a little tidbit here, because you have to be careful with dealing with these chemicals. And so these are some of the additives: methanol, ethanol. I don't know what happened to those. I guess that's tert-butyl ether, TBE. I had some scribblings on these. I tried to hide them, but looks like it hid the whole thing. These are examples. Now, what's really interesting, look at the octane ratings of all these chemicals. 115 for methanol. Ethanol is about 124. MTBE is 115. ET, ethyl tert-butyl ether. TAME is tertiary amyl. Tertiary, it's a C5 methyl ether, and then DIPE. So all these ethers, you have very high octane ratings, and so most refineries like to add them because it increases your octane. You're selling octane. If I can get up to 92, I can sell it for 20, 30, 40 cents more. So they're always trying to beef up the octane. But what was interesting is that when we used to add MTBE, look at how much volume percent we could add without affecting the vapor pressure, which was a key component. Okay, I mean, what controls the volume percent additive? This is the spec, 2.8% oxygen, and there's a reason why we picked 2.8%. But the government regulates the gasoline to make sure that every gallon you put in has at least 2.8% oxygen in, and a little over a year ago, 2 years ago, we used to be able to add almost 11% by volume MTBE. So that's a large volume of MTBE. There's a big market for MTBE. With ethanol, the problem with ethanol is it's not shown, the RVP. You see, MTBE had a low RVP. So if I blend 11%, the RVP doesn't get too high. But look at the ethanol. The RVP is 15 to 20. It's very high reed vapor pressure. So you can only add so much until you get to the 20% and affect the overall vapor pressure of the gasoline. And what that did, created another set of projects for us. Of course, every time the government changes the spec, that's more business for us. We have to go, and you remember I was saying how much butane, I don't know if you remember the past charts, there was like a 7%, we can add 7% butane into these gasolines, but if you add 7% gasoline, that butane, the RVP is high, and then I add another component that has a 15 to 20, you're going to, basically mess up your spec. And so we had to depentanize, in other words, remove the butane and pentane from the gasoline blend. And that created a nice set of projects for us. And so what we did is we ended up removing the C4s and C5s out of the gasoline blend in order to satisfy this 2.8% oxygen. So in the summertime, we're removing pentanes, butanes and pentanes, and it's a large volume. And so luckily in California, we have these salt domes, caverns. They used to mine salt in the old days by pretty much injecting water. And you get the salty water comes out, you evaporate it and produce salts that we use for table salt. And we have these big, huge caverns of salt domes. And so what they do now is they basically pump gas, this pentane, butane, pentane mix down these holes during the summertime. And in the winter, we're pumping it back out again, inject water, pump the gasoline, this pentane stream out, and blend it back with the gasoline. Or you have to build a big, huge sphere under pressure, because these are high vapor pressure components, and store the butanes and pentanes. Same thing with, or store it under atmospheric pressure, but we have to put in refrigeration packages. So there were two ways. We designed actually the one at Benicia Refinery was a refrigerated package, so it's an atmospheric tank, but it's cold, or under pressure in the Shell Wilmington. There's a big 84-foot sphere there. Okay, so the future of oxygenate blends, again, the price of oil dictates the price of methanol and ethanol. Obviously that's coming down because a lot of now with the issues with what do they call it? I mean, regenerative fuels that you can cultivate out of corn and so on. That's becoming popular. So ethanol now is gaining popularity. Production use of incentives to encourage the government to produce renewable sources of energy. And then federal and state mandates like Colorado, Arizona, New Mexico, and Nevada, they have certain mandates for adding or not adding oxygen material. Then detergents, as I told you, they improve your carburetor performance or your injectors. They clean them, or they help the intake valves or ports. You know, they help clean your engine. Nobody uses carburetors anymore. I think today, in 1990, pretty much all the cars, 85% is fuel injection. Clean fuels. These clean fuels, you had the Clean Air Act that was signed into law in 1990, and it controlled the aromatics, benzene for sure, because benzene, of course, was deemed a carcinogen. It does cause cancer if you're exposed to high levels of benzene. So, of course, the refiners kind of had to bite their teeth about that one because benzene had a very high octane rating. It has a very high octane rating. Oxygenates and detergent additives, these are our specifications. The auto oil program, there's a consortium of 14 oil companies and 3 auto companies that get together, and they have research programs to improve both the specifications for the fuels as well as the cars, the design of the engines themselves and how it impacts that. The Clean Air Act requires this oxygen mandate, so they looked at different blends, and they found that the oxygen at 2.8% actually produced the lowest NOx. For some funny reason it goes down to a minimum low NOx, and then if you start adding more oxygen, the NOx starts coming back up again. So that's where that 2.8%. Benzene, it's limited to 1% by volume, so you can't produce, or you can't blend any more than 1 volume percent. And then the aromatics, 25 volume percent. That's the limit on the amount of aromatics that are allowed in a blend. So you have to find ways of, because of course, it'll reduce your volatile organics, it'll reduce the toxic components such as benzene, and the NOx, minimizes NOx. There's an example of a car. You got emissions from the engine itself, leaky valves and leaks and things like that. Refueling, I talked about the refueling and the bellows and how when you're injecting the fuel you're recovering that. And of course the exhaust, that's why you go every 2 years and get your car re-certified to make sure that the emissions don't exceed the allowable limits. Okay? Non-attainment, these are areas where the ozone level has exceeded, and you'll notice they're really the highly populated areas where I think there's just too many cars. Okay, and so there are certain mandates by the government to meet ozone levels, and the black spots there, and if you go check out the maps really, you'll find out these are heavily populated areas where there's too many cars. So there's a lot of hydrocarbon emissions of volatile organic hydrocarbons that produce these non-attainment, which means that they cannot maintain oxygen ozone levels low enough. Okay? And this is a picture that shows you what forms this ozone problem. And hydrocarbons plus nitric oxides form ozone. There's some chemistry here in a minute that will explain that. Here you go. So the nitrogen oxides react in the presence of the ultraviolet lights, will form NO. It'll break it down to nitrogen oxide plus an oxygen radical. That oxygen radical is very active, reacts with air, and forms this ozone, O3. And that's how really ozone is formed. The ozone can then go back and oxidize. You can force it chemically to react with nitrogen oxide and go back and produce NO2 plus oxygen. So ozone concentrations are proportional to NO2 to NO concentration ratio. There's some more volatile organic compounds. These, with the OH radicals in the presence of air, will produce water plus a more complex hydrocarbon molecule known as RO2, or the RO2 will react with the NOx and form an NO2 plus water plus carbonyl. And those are those black particles that you see in the air that you can't see through because they're bigger molecules of hydrocarbon. So really these volatile organic compounds, they react to form much larger molecules that you can't see through. And it forms that layer of, anybody flown, come down with an aeroplane coming down, you'll see that you've really going through a black cloud pretty much. The auto oil program, that's a continuous exercise in developing different. What's funny though is that, you know, with California being a heavily populated area, and we have these highly specialized, the specs for the gasoline is very tight, to the point that many other states don't produce our gasoline because they don't have to. Okay, and so when you get an accident like, you know, a refinery shutting down, there's a shortage, we can't make up the balance by just saying, oh, let's go buy more gasoline from somewhere else. That can't happen overnight because of these tight specs that we have here, unless, you know, the governor interferes and decides to relax the specification. Okay? Distillate fuels, keep going. Let's take a break. You want a break? Yes? No? Keep going? Okay. These are planes, the SST Concorde. I think they discontinued those planes after that bad accident they had. Just a comparison of the cruising speed, 2.1 Mach versus 0.85 Mach. Passenger loading, about 118, to about 400, 600 people probably in a plane, and these Boeing 747s, the long ones. How much fuel capacity? 51,000 gallons. Fuel consumption, 3,700 gallons per hour. That's how much it consumes per load. So you can estimate how far it can go. Obviously, it can only fly for about, what, 10, 15 hours, which is about from here to Australia. Okay? After that, there's no gasoline, no jet fuel. So it consumes about 38 miles per gallon per passenger. Sometimes 600 or 400 passengers, that will tell you roughly how much gasoline you consume per mile. Okay? Commercial type fuel, they use the Jet A and Jet A1. And these are just different grades of fuels that go along with the different engines. Jet fuel specs. Yeah, jet fuel, again, volatility, density, corrosiveness, and then cleanliness. That's a picture here for a jet engine. Yeah, it's a combustor and a turbine blades, so it expands and produces enough power to move an engine, move a machine. Aviation fuel distribution, there's a refinery, you pump it to fuel storage. It goes through clay. Clay is used for drying the fuel. Remember I talked about freeze points and how these fuels cannot be wet. It has to be really dry, bone dry. So we run them through clay beds to absorb any water. Because in crude towers and fractionators, we use a lot of steam. We inject steam in order to help distillation and fractionate these fuels. And it goes through distribution, where you pump them again through more clays. Goes to a terminal, and then from the terminal to the airport, and then from the airport it's pumped through some hydrant truck to the airplane. It's supposed to be an airplane with jet engines there on the side. That's the wing. Okay. Fuel requirements, typically, of course, good burning characteristics, flow, safe, clean, stable, and uniform. They do add stabilizers, dispersants, flow improvers, metal deactivators, and then corrosion inhibitors all the time. Diesel fuel requirements. You want good starting properties when you turn it on. Diesel is notorious for, I mean, you can tell a diesel engine just by listening to it. But lately, I have to be fair, the engines have improved so much that I was in Bulgaria, actually. We have a big office in Bulgaria, by the way. And well, I spent almost all day. We traveled about 250 kilometers one way to the refinery and then back in the evening. About 3-hour trip each way. And on the way back we were having dinner, and the driver says something about, oh, my car, I like diesel engine. I'm saying, what do you mean diesel engine? You mean this was a diesel engine? He says, yeah, that was a Renault diesel engine in a Renault car. And there's no way I could have told that that was a diesel engine. It's just so smooth and just very powerful. So they're pretty reliable machines. So I don't think this starting issues is a problem anymore. They've been able to get around it.